Hey guys! In the last video we looked at parent functions, some basic parent functions, and we're going to continue now looking at transformations of functions and then apply it to those parent functions. Okay, so I'm going to start out with, we had studied extensively the graph of f of x equals x squared, the parent function for quadratics. It looks like this. The vertex is at 0, 0, 1, 1 is on the graph, 2, 4, negative 2, 4, 1, 2, 3, 9, because when we square those numbers, we get whatever x is, the y value would be that number squared. So we have the basic parent function there. And then let's look at some transformations that we've already studied. So recall that we did an investigation on what happens when you add or subtract a number inside the parentheses before you square it. And if you recall, it made the graph of our parabola, instead of our vertex sitting there at 0, 0, the graph shifted 2 units to the right. So the vertex is over here now at 2, 0 instead of 0, 0. So notice when it's inside the parentheses, we shifted to the right, not to the left, which it seems like would make more sense. But actually, if you think about what would make the y value equal to 0 is when x is 2. So that's why it shifts to positive, in the positive direction, 2 units. Okay, here's another example. If you have the graph of the parent function f of x equals x squared, and we want to graph a transformation of the function where we have x squared minus 4. Recall that that shifted the vertex down 4 units. So instead of being at 0, 0, it's now at 0, negative 4. So subtracting within the parentheses was a shift left or right, and outside of the parentheses after squaring, it shifted down 4 units, or if it was plus 4, it would have been up 4 units. Okay, this next one here, this is actually going to impact the shape of the graph. Remember that this is going to be a vertical stretch. At the a value, remember if the a value was a number bigger than 1, we kind of talked about it as making it look more narrow, but really what it is a vertical stretch. All of the y-coordinates get stretched twice as tall, so it's a vertical stretch of factor 2. And this minus 1, since it's after the squaring has happened, is going to be, it's going to shift the whole graph down 1 unit. So the vertical stretch, 0, all the y-coordinates get stretched twice as tall. 0, 0 is going to stay at 0, 0, because 2 times 0 is 0. But instead of 1, 1 being on the graph, it's going to now be up here at 1, 2, and negative 1, 2. And 2, 4 becomes 2, 8. So it got stretched twice as tall. It's called a vertical stretch. And then shifted down 1 unit. So the graph would look like that in the end result. And then you can have combinations of transformations. In this case, we have a negative in the front. Remember when that a value was a negative, it flipped the graph upside down. So instead of 0, 0 would stay there, but instead of 1, 1, it'd be 1, negative 1, a negative 1, negative 1. And so everything, all of this entire graph will get flipped upside down. So, and since I have a smart board, I can do this quite easily. It's going to look like that. And then we have this plus 3 inside the parentheses. So think about what that did. Remember, it moved it to the left 3 units. And the plus 2 after the squaring moved it up 2 units. So I'm going to take this purple graph I have, and I'm going to drag this vertex 3 units to the left and then up 2 units. And the shape of the graph hasn't changed. But it is flipped upside down and shifted left and up. Okay, so I want you guys to be thinking about what all of these different things will do to the graph. Multiplying by the 1/2 in the front is actually all of the y coordinates get compressed. They're all going to be half as tall. So this is called a vertical compression. When we first started learning about it, we described it as being wider, but it's really like less tall, shorter, I guess. Vertical, it's a vertical compression of factor 1/2. And then this -2 shifts it to the right 2. And then the -4 on the outside shifts it down 4. So let's compress this so that it's half as tall. So instead of 0, 0 will still be 0, 0, but instead of 1, 1, it's going to be 1, 1/2. Instead of 2, 4, it'll be 2, 2, and -2, 2. Instead of 3, 9, it's going to be 3, 4.5, half of 9. And then 4, 16 would become 4, 8. So I can fit that on my graph here. So I'm going to include that point. And it looks wider, but it's actually being compressed downward. And then we're going to take that graph and we're going to move it to the right 2 units. So I'm moving that vertex to the right and then down 1, 2, 3, 4. Transformations are a lot easier to do when you have a smartboard. Okay, so in summary, these transformations hold true for all of the functions that we're going to be studying in this class and next year in pre-calculus. So I want you to take a moment and write these transformations down. I'm going to go through them here, but if you need more time, just pause the video as we're going along. So if you have a function f of x, and if c is a positive number, then, oops, whoa. Okay, first transformation we're going to talk about is if you have a function f of x, so now I'm generalizing this, so instead of x squared, it's any function. It could be, and the parent functions we looked at were linear functions, quadratic, cubic, square root, and absolute value. So if you, like for example, if you had the absolute value of x, if that was the function, and then you add a number after you take the absolute value, so not inside the absolute value, but absolute value of x and then plus some number, it's going to be a vertical translation up c units. So whatever number you added is going to shift up that many units. The next one, if you subtract c, so for example, the absolute value of x minus 3, it's going to be a vertical translation down 3 units, or in general, c units down. If you have a function and you add a number inside the function, so if you were talking about absolute value, if you had like the absolute value of, let me write some of these down, these examples down that I'm talking about. If you had, let's say that the function is the absolute value of x. If I were to add a number so that now I have the absolute value of x plus 2 inside the absolute value, that is going to make the graph shift to the left 2 units. So inside, like when we had the squaring, it was parentheses when you subtracted a number inside and then squared, or added a number, I mean, it moved it to the left. And then if you go and subtract a number inside the function before you do the function, it will be a horizontal translation right c units. So notice when you're adding a number or subtracting a number after you've done the function, outside of the function, it was a vertical translation. Inside, before you do the function, it's a horizontal transformation. Okay, there's more here. So this next one, if you multiply by a number c on the outside, anything that's on the outside is going to affect the graph in a vertical manner. Anything that's on the inside of the function is going to be horizontal. Anything that is vertical is kind of like directly how it seems like it should be. If you multiply by a number c, it's going to be a vertical stretch. It's going to stretch all the y coordinates c units taller. If c is greater than 1, it'll be a compression if c is a number between 0 and 1, like a proper fraction, like 1/2, 1/3, etc. And it's called a vertical stretch or a compression, depending on the value of c, of factor c. So whatever c is, it'll be a stretch or a compression of that value. Now the next one, if you multiply by a number inside the parentheses, so inside is going to affect it horizontally, that'll be a horizontal stretch or compression of factor 1/c. Just like when you added or subtracted a number inside the function before you do the function, it moves it the opposite direction that it seems like it should. Anything horizontal is always kind of messed up, like, or it doesn't seem like intuitive as much as the vertical does. But if you multiply by a number inside the function, and I'll do some examples of these in the next video, it's going to be a horizontal stretch. If it's a stretch, if c is a fraction now, notice that's opposite of what it would be if it was vertical. It's a compression if c is greater than 1. So between 0 and 1 is a stretch, a horizontal stretch. And if c is bigger than 1, it's a compression of factor 1/c. So you're going to take the reciprocal of whatever c is. And every x-coordinate will be, if it's a stretch, every x-coordinate will move out by that multiplier. And if it's a compression, it'll be cut by that multiplier. Okay, next one here. If you have a negative on the inside, it's going to reflect over the y-axis, which we know the y-axis is the vertical axis, but when you're reflecting over that, it's actually a horizontal reflection. It's just going to turn horizontally. So if it's a negative being multiplied on the inside, it's a reflection across the y-axis. And then the last one here, if you multiply by a number on the outside of the function, it reflects it across the x-axis. So it's a vertical reflection because it's going to flip upside down. Okay, so that is, I'm going to stop here, and in the next video I'll go over some examples of how this works for just any kind of function in general.